All right, so we are going to look at, I guess over here, Bootstrap confidence intervals. Okay, so we'll start off by just loading up the data. This is the law school data. This is the random selection of 15 law schools out of the population of 82 law schools, and we want to know what's the correlation between LSAT score and GPA. Okay, and so the true relationship between LSAT and GPA is the relationship in the 82 the full population of 82 schools, but this data set law just represents a random selection of 15. Okay, and we showed how to use the boot function as part of library boot, which involves us loading a function called the statistic function, and in our case, the statistic we're calculating is the correlation, and that involves taking the data and a vector of indices, right? And so we subset the data based on the vector of indices, and then we return the desired statistic of that subset data, which in our case is the correlation. Okay, and so we can run this, and we will get our Bootstrap object, and our Bootstrap object looks just like this output right here. It says, in our sample of 15 law schools, the correlation is 0.776. Our estimated bias is this, and our estimated standard error is this. Okay, so this is just ordinary Bootstrap. And once we've created a Bootstrap object, we can perform some inference and produce some confidence intervals. Okay, and so these there are 5 confidence interval types that we'll talk about. The first few, the standard normal, these are all Bootstrap confidence intervals, and they're all like, why are there so many confidence intervals? But we've got the standard normal Bootstrap, the basic Bootstrap confidence interval, the Bootstrap percentile confidence interval, the studentized Bootstrap confidence interval, are also known as the Bootstrap T interval, and the adjusted Bootstrap percentile interval, also called a BCA confidence interval. It's well, we'll talk about each of these, and is one better than the other? They're probably, this last one that we'll cover as the quote nicest theoretical properties, based on the works of other people, but we'll talk about these. Okay. So the standard normal here. Let me open this up in Firefox here. Okay, so the standard normal Bootstrap confidence interval looks just like a regular old confidence interval. So if you were to make a confidence interval for the sample mean, not the sample mean, for the population mean based on a sample mean, it would look something like this, right? You would put x bar, your estimate of the parameter, so your theta hat, in the middle, plus or minus a z star value. So 95% would be 1.96, or 90% would be like 1.645, times the standard error. Okay, and so when you do the standard normal Bootstrap confidence interval, you just take your sample statistic. So in our case, it would be the kind of like the correlation of the entire sample of 15, and then you would use the Bootstrap estimate of the standard error right here as this. So it would be your the R from your sample plus or minus 1.96 times the estimated standard error. And that's your standard normal bootstrap confidence interval. That feels straightforward enough, right? That's question?
Yeah, so for this one, the theta hat,
Yes.
is it the true one from our sample or just the bootstrap mean, the mean of the bootstraps?
So yeah, this is the in our sample of 15. This is the statistic based on that sample of 15. Okay. Now the mean of the bootstrap estimates, if your estimate is unbiased, should be the same as this. Okay. But the well, actually, I guess the bootstrap will point this out. So in our case, we would be using this. This is based on our. It would just be as if we took our, our data law and we did law column 1 and law column 2. Whoops, I got to stick that in the correlation. And then so this goes in our center here. Okay. And so that's the standard normal bootstrap confidence interval. The basic bootstrap confidence interval. So this one gets a little bit more odd, but your lower bound is twice the estimated statistic minus the 1 minus alpha over 2 quantile, and then that's the lower bound, and then the upper bound is twice the statistic minus the alpha over 2 quantile. So you'd be subtracting off, so you're doubling the statistic, and then you're subtracting off basically the, for a 95% confidence interval, then 97.5 percentile or quantile, and you're subtracting off the 2.5 quantile. Okay, so why is this? I've tried to explain it here. We'll see if it makes sense. So we can pretend we have like the parametric case, okay? And we'll say T is an estimator for theta, okay? And we're going to, what we do is we're going to transform all of our things by doing T minus theta, okay? And so we're going to assign this value A sub alpha is the alpha quantile of the quantity T minus theta, okay? So if you're following me so far, then this is just the definition of a quantile. So if this is the alpha quantile, then T minus theta, this is, a random variable. The probability that this quantity is greater than this is going to be 1 minus alpha. That's what it means to be the alpha quantile. Okay? And then so if I just move this over here, swap this and this, and I just kind of move terms around inside this thing, I've got T minus the alpha, or A alpha quantile of A being greater than theta, still equal to 1 minus alpha. Okay? And so based on this, our confidence interval, the upper bound is going to just be T minus A, and then following the same logic, our lower bound will be T minus A for the with T minus the 1 minus alpha quantile of A for a 1 minus 2 alpha interval. So if alpha is 2.5%, so here we would subtract off the taking our estimator of theta, and then we're subtracting off this quantity A, which is T minus theta. So so the way we would do this with non-parametric bootstrap, okay, we don't know the distribution of T, okay, but we can kind of build up this distribution of T via bootstrap replicates. All right, so with bootstrap replicates, we generate a bunch of these bootstrap values of theta hat, okay, and we arrange them from least to greatest, and that kind of creates an empirical cumulative density function, right? And based on that empirical CDF, we can get the alpha quantile of theta hat. Okay. And then so just making the parallel argument over here, instead of using t, our estimator of this quantity theta hat star, we can assign to this quantity b sub alpha. All right, where theta hat star is our bootstrap estimator for theta hat. Okay, and then so just using the same line of thinking that we have up here, our b hat sub alpha is equal to theta hat sub alpha minus theta hat. Okay, and so plugging this into our upper bound and our lower bound, we would have theta hat minus b hat sub alpha equal to this thing, which gives us the upper bound of the confidence interval, 2 theta hat minus theta hat over alpha. Okay, and then so just adjusting that so that we have a 1 minus alpha confidence interval, we divide our things by 2. Oh, and yeah. Okay, so this is the basic, I don't know why it's called the basic Bootstrap confidence interval, but that's what we have. And then the Bootstrap percentile confidence interval, this is the easiest. You just have all of your theta hats and you arrange them from least to greatest, and then you just take your alpha over 2 quantile and then your 1 minus alpha over 2 quantile. Yes, question?
What does the basic bootstrap, I guess, tell you in like its formula that like the other bootstraps don't?
Yeah, as far as, so the question is, why would we use one confidence interval over another confidence interval? I don't know. The answer is, yeah, I guess just these different confidence intervals have kind of evolved and they exist, and the selection of which one to use is it's a little. I think that one's harder to explain. So, yeah, I'm trying to think what exactly the basic Bootstrap confidence interval tells us that the other one doesn't. So I guess the disadvantage of this confidence interval is that it kind of depends on this normality assumption. Okay, the disadvantage of this one is that it depends entirely on your Bootstrap estimates. Okay, and this one, I mean, it also depends very much on your Bootstrap estimates, but what is the reason here? There's kind of maybe a little bit of an intuitive sense that if we're using this the difference between our I want to say this one will give us something that's a little bit more centered as far as, so if your Bootstrap estimates are a little bit more skewed, that's going to kind of be reflected in this thing, whereas this one is going to be a little bit more centered-ish, I guess. When we once we've created our Bootstrap object, R can spit out these confidence intervals very easily. You just feed it the Bootstrap object, which is the results that we from earlier, and we just feed it into the function bootci, and it will spit out, and we say, we want the normal one, the basic one, or the percentile confidence interval in it, and it spits these out. Okay, and we can kind of verify that the answers that R gives us matches, I don't know, the formulas that we have for each of these things. Okay, and so we can kind of compare how these confidence intervals go. Okay, and so when we create the Bootstrap confidence interval for the using the normal, okay, our confidence interval for the correlation goes from 0.5 to 1.046, okay? And so clearly it can't go this high, right? Correlation maxes out at 1. But this is what we get here, okay? The basic interval also goes over our upper bound of 1. And the percentile one is based just entirely on our Bootstrap estimates, which means because the Bootstrap estimates will in of itself not go over 1, this one doesn't. Okay, so we see these things. If we created the normal confidence interval ourselves, we get a slightly different set of answers here than what this one does, and that's because the R formula adjusts for bias. Okay, so we get something a little bit different, and I'm actually not entirely sure the formula it uses to adjust for bias in this thing. Okay, but the basic confidence interval, okay, is we're taking the estimated theta hat, okay, and we double it, and then we're subtracting off the quantiles of that we get from our Bootstrap intervals, okay, and then over here we just we're just calculating from the quantiles, okay, and there's several ways to calculate quantiles, and so the one that matches up with what R gives us with this thing is using type 6 of the quantile calculation. So yeah, calculating quantiles is always a little bit of a thing for contention. Okay, I don't know. And so, you know, if we look at, you know, the properties of these things, all of these confidence intervals, they seem to vary quite a bit, right? And that's just, I guess it's hard to say, you know, which of these perform the best and which of these perform the worst. You can kind of, I guess you can try a bunch of experiments and see, try different samples and create a bunch of, you know, basic confidence intervals versus percentile confidence intervals and see how they perform versus the population statistic. But, you know, based on our sample of 15, our intervals are going to be fairly wide also. Okay. The other two confidence intervals, okay, so that covers the kind of the first three, and then we've got the studentized Bootstrap confidence interval and the adjusted Bootstrap percentile confidence interval. These ones are a little bit more complicated in their calculations. Okay, so I'll describe this one, the Bootstrap T interval. Okay, whoops, I messed up something here. So what this is saying is that even if the distribution of theta hat is normal and unbiased for the true value of theta, okay, normal distribution is not quite correct because we're using the z statistic when in fact we don't really know the distribution of theta hat and we don't know the true value of the standard error, and so we just have an estimate here. Okay, and so when you did created confidence intervals for like the sample mean, you adjusted for the fact that your standard error was estimated by using the t-distribution, right? But we technically can't do a t-distribution because the distribution of this Bootstrap standard error estimate is also unknown, okay? And so we're going to, it's called the t-interval or maybe a studentized, okay? And so we're going to basically do a bootstrap within the bootstrap to get an estimate of the distribution of the standard errors. Okay, so when we perform bootstrap, we get an estimate of the standard error of theta hat, but then to kind of get an idea of the distribution of this standard error, we're going to perform a bootstrap within the bootstrap. Okay, so basically, if you're going to do a bunch of replicates, you start off by calculating the sample statistic based on your entire sample. That's your theta hat. And then for each bootstrap replicate, you start off by doing a bootstrap sample with replacement, right? So that's normal. And then you calculate the theta hat from that bootstrap sample. Okay. But then once you have this, you're also going to perform a bootstrap by computing the estimated standard error of this sample. Okay, so you're going to repeatedly perform bootstrap of this bootstrap sample. So you've selected points with replacement, and then from there you're going to select points with replacement again to get an estimate of this standard error here. And you store this as the t. I've got another typo in here. You store this as the estimate of t, and we're going to keep track of all of these standard errors here. Let me fix this. So the t is what happened here? Correction. There's something wrong with my... Okay, so that looks better. Okay, so this is your standard, your t, you do take the difference between your estimate versus kind of the mean divided by the standard error. Okay, so we do this for every single bootstrap, so if you're doing a whole bunch of these, it's going to take a long time. Okay, so if you have 1,000 bootstrap replicates and if this thing is done, you've got 1,000, then you're essentially doing 1,000,000 bootstraps, right? Because you're doing 1,000 bootstraps within these 1,000 bootstraps. So it could be computationally very expensive. Okay, and then so we keep track of all of these, and basically we get an empirical cumulative density function of our t statistics. Okay, and so this will serve as how we will choose t star alpha and for the plus and the minus. Okay, our t stars there, and then and as far as the standard error of theta goes, that just comes from our entire bootstrap. So yeah, where let me see what happened here. Okay. So we get the the standard error the normal way from Bootstrap. Okay, and then we can compute the confidence limits. Okay. So here's some code that implements doing the Bootstrap t interval. It's a little messier. Okay. So on the outside we define kind of the big bootstrap, and then so this is how many B bootstraps we do, and then this R is how many bootstraps we do within the bootstrap. Okay, so to get the estimate of the standard error of each standard error estimate. Okay, so we we just take our data and then we set storage places for the statistics and the standard error. Okay, and then to calculate the bootstrap standard error, this is its own function taking the data, not the original data, but this will be the data that has been selected via Bootstrap. Okay, so we can see that this will be fed, and then we do R 100 or whatever it is replicates to get the standard error. So this is just a regular old non-parametric bootstrap to get the standard error of some sample X, right? Okay, and so in this case, and this is the big loop for the bootstrap. You take a bootstrap sample from 1 through n with replacement. You subset your data. You subset your data X, and we're going to call that Y. The bootstrap estimate based on that subset, or the bootstrapped random sample, is going to be we apply the statistic function. The statistic is the whatever function it is to calculate the statistic that we want, and then we estimate the standard error by running the bootstrap standard error function inside of this. Okay, and then so you can see we feed the bootstrap standard error the sampled data Y, not the original data, which is makes sense. Okay, and then so we take all of these findings and then we combine them to get our confidence interval. So we estimate our t statistics, the difference between each statistic and the null statistic from the entire data set divided by our standard errors. So this is vectorized, right? Stat here is like 500. There's 500 statistics calculated minus the mean, or not the mean, but the one from the entire sample, and then there's also 500 standard errors calculated. So we get 500 t statistics, and then so the standard error that gets put in the that we use here is just going to be the standard deviation of all of these statistics. That's their standard error. But then our choice of the t stars are based on the quantiles of the t statistics that we've calculated. Okay, so it works, and I guess I can run it. Just because I didn't, for efficiency, I didn't want it to render every time I ran the code, but we'll do it. And so here we can look at that patch data, comparing the ratio of the mean of Y over the mean of Z, and we can apply the Bootstrap CI here. So we'll try running this. Run that. So it's running. It's going to do 2,000 Bootstrap replicates and 200 replicates inside. So that's what is that? 400,000. Okay, so it finished, and let's look at our confidence interval. Oh shoot! This is what it produces for the confidence interval of mean of Y over mean of Z. I suppose we could do it for the law school example. And so in our case, our data would be law, and then our statistic will be the correlation between the first and second columns of data here. Right? Did I mess something up? Okay, so I think if I just ran stat on law. Okay, so that works. All right, so we will we'll try running this. So this is now for the law school. We'll create our confidence intervals. We'll see what it produces if it finishes. What happened here? Quantile t-stats alpha type equal 1. NAs. I'm getting NAs here. Why am I getting NAs? Let's just do fewer and see if we still get the same. There were 42 warnings, error in quantile. What happens if I ask for this? Yeah, it didn't work. I've got not NaNs in my t-stats. Why would I have that? Stat 0. Okay, so somehow I bet my standard error is, somehow the standard error is coming out as 0 in some of these functions somehow. Let me see. The standard deviation is 0. Correlation in data 1, 2. Yeah.
If it's calculating the standard deviation like based on the data there, like isn't there a slight chance that you get every number the same? Like you get the same operation over and over again, and then because of that there's no standard deviation?
I mean, it is possible, but I feel like that's so incredibly unlikely. If I'm doing, 200, let me just, that is possible. Okay, so my data is, oh, wait a second. Is this right? Did I not do this correctly? Oh, I didn't load the data. Okay. Oh, well, that doesn't look right either. I'm getting a negative correlation here. Is that possible? So wait, let me just look at my data. Okay, so data is this. It's our LSAT GPA. We're doing this. All right, I'm gonna just run this thing. I'm getting a negative correlation on my lower bound.
Does score compute R or R squared?
Core computes R. I mean, yeah, I could have a negative correlation, but I would be quite surprised if that's going to tell me that that's possible. I hate everything. Darn it. Okay. Yeah, I'm still getting something negative on the lower bound here. How can that be? Okay. I don't know what's going on. I'm pretty sure I've implemented, well, so I'm using, the code was actually written by Maria Rizzo, and I'm pretty sure she wrote it correctly. I'm looking through it. It seems to make sense. I don't know why I'm getting a negative number. I feel like something has gone wrong, but yeah, I don't know. I don't know what's going on. Okay, let me just comment these out so it doesn't give you errors when you at least render the text to read. Okay, the other interval is the BCA interval. Okay, and BCA is the bias corrected and adjusted for acceleration interval. It's basically the adjusted percentile interval. So we're picking percentiles, but the way we pick our quantiles is we're using alpha 1 and alpha 2. Okay. And we're using these crazy formulas to pick out our alpha 1 and our alpha 2. I'll tell you what these are, but I couldn't tell you how we got these. Okay, so this term z hat sub 0, this is kind of like a bias correction, and if theta hat is the median, then z hat sub 0 is 0. Okay, but if theta hat is anything other than the median, you're going to have something that's a little bit different from 0. Okay, and it's kind of the, where, if you're thinking of an inverse normal, right, phi, so you guys know that phi is the p norm function, right, the CDF of the, so little phi is the normal density, and then big capital Phi is the, it's basically what your z table gives you, right? So capital Phi of 0 will give you 0.5. Capital Phi of 1.28 gives you 0.9. Okay, and then phi inverse just does the opposite. So if you look at phi inverse here, if theta hat is the median, then all of these, I is the, I don't know if this thing makes sense to you guys. I is the indicator function, so it's basically just turns this expression into a yes or no. If your bootstrap estimate is less than theta hat, you get a 1, and if it's greater than theta hat, you get a 0. And so if theta hat is the median, then half of the bootstrap estimates will be 1, and the other half will be 0. And then so if you do 1 divided by the total number of bootstrap estimates, this entire quantity inside the big parentheses becomes 0.5, and then phi inverse of 0.5 is 0. What z-score gives you an area shaded to the left of 0.5, that's 0. Okay, so this is the kind of the bias correction part. A hat, this is not alpha, but A hat is an acceleration factor. And I am not sure how they came up with these exponents. We're taking kind of the difference between the mean jackknife and each jackknife estimate, and we're raising it to the third power, and then on the denominator we're taking that and we're doing something else to it. I don't know. Don't ask me how they got these. Okay, but it's established in the literature, and apparently, if you use these to pick out your confidence interval bounds, they have a couple nice properties. Okay, and so the nice properties of this bias corrected or the adjusted percentile interval is that if you transform your statistic or the parameter, then the corresponding interval is just the transformation of your your bounds. So you find the bounds according to this, and you transform it, and you get the correct bounds as well. And then the confidence interval is second order accurate, which just means that the error rate of the confidence interval that the error will tend to 0 at a rate of 1 over n. So all confidence intervals get better and better as your sample size increases. Some of them get better at a rate of 1 over the square root of n, which is first order accurate, and then this one gets better at a faster rate of 1 over n, and that's second order accurate. Okay. So apparently, these are nice things. Okay. Again, Maria Rizzo wrote some code to implement calculations of the adjusted BCA interval. Okay. So basically, it's just finding all of these formula versions of all of this. So we can do this. This is for the patch data. But we can also do it for kind of the for the law school data as well. Okay, so for the patch data, this is how the two things compare. So this is the regular old percentile interval, and then if you adjust the percentile interval using this, you get slightly different bounds, which apparently these, in the long run, behave better. But let me just run these also for our law school example. So x here will be law, and we'll do this. My statistic is, let me get this from up here. So there it goes. Okay, well, it said something might be unstable here, but okay, so this is the Bootstrap confidence interval for our our law school thing, and so creating a 95% confidence interval based on just the percentile of our Bootstrap estimates, we get this, and then when we adjust it, we get something else. Okay, and so we've covered like 5 different Bootstrap confidence intervals. And they all seem to behave, quite a bit differently, at least on the bounds, right? And so we have this question: which confidence interval should we use, and what kind of inference can we make? And the answer is, it depends, which is always the answer in statistics. And I hesitate to kind of give you any hard and fast rules. I think you can kind of create all 5 of them and just kind of say like, all right, well, where do all of these kind of overlap, and get an idea of where you're like especially confident. Yeah, well, okay, yeah, that will be like the yeah, that would be your confidence level would be less, but in terms of like what's a plausible value for the true parameter, then that would be plausible under all and for all confidence intervals. But then of course the width of that is going to be the most narrow, and so you are least confident in terms of the final conclusion. And if you want to be most confident, you got to go to the the most extreme upper and lower bound, but then you kind of have this super wide useless interval, right? So, you know, if we think of the big picture of a confidence interval, and you know why we're using Bootstrap in the first place, I think it makes sense that our answers are not going to be very good, right? So with a confidence interval, the idea is you're looking at your sample, you look at the variation within the sample, and based on that, you want to make a statement about the population parameter, okay? And so right now your best guess is the corresponding statistic from the sample, and then the width of that interval is based on the variation that you see in the sample. That's kind of the big picture in the confidence interval. With Bootstrap, we're unwilling to put any assumptions about the population or the population or the sampling distribution of the parameters, or I should say statistics. And so because we're unwilling to put any assumptions on it, all of our inference about the distribution of the population has to come from our sample in of itself. And so, you know, the conclusions we make are going to be even less powerful. They have to be even more vague, the conclusions we have. And so I think each of these different intervals that we're creating with Bootstrap kind of are hoping one thing or another, you know? And I guess based on, you know, the first one is kind of hoping that there's a little bit of, like, the normal distribution can kind of be assumed at some point. And so that's going to create certain boundaries. If you say, well, that's not the case, you know, let's look at this or let's look at that, you're going to get different boundaries. And so I guess they all reflect just a little bit of, or a lot of the uncertainty that exists when you're trying to make conclusions about the entire population based on just the sample that you see. Okay, so anyway, these confidence intervals exist for Bootstrap. As always, think through what you're doing and what the implications could be, rather than just saying, oh, let's write this line of code and see what it spits out and go with that. So okay, we'll end there. Have a good weekend. We'll see you guys on Monday, and that will be the only class we have next week, because Friday is holiday and Wednesday I'm canceling, so